Okay, I previously started the basics of the scientific understanding of climate change, and I just covered a few things. So far, we know that climate always changes. We've known that since 1824, and we know that some gases are important. We've known that since like the 1850s. Um, we even saw it coming. There was a guy who knew that CO2 could affect climate. And so we've actually been collecting evidence of rising CO2 levels that are correlated to rising temperatures since about the late 1950s. This guy's a name you need to know, Keeling, Charles Keeling, and he made this really famous data set called the Keeling curve. Anyway, we also know temperature records that go really far back because even before we had thermometers, we can analyze which gases were in the atmosphere, and that's a very good way to know the temperature of the atmosphere. We can analyze samples of pollen found deep in lakes, and that's a way to see if temperature had been rising or sinking backward through the historical record of pollen. And we can look at sediments that are found underneath the South Pole. Also, geologically, these can tell us temperature records going really far back. And we know with really solid evidence, climate has been following this really stable long-term trend. We had an ice age that finished about 15,000 years ago, took about 5,000 years to get to a relatively high temperature. Then it's been going downhill for about 6,000 years. And all of a sudden, something weird started to happen right about there. Something really weird. Today, we're up there somewhere. Something really weird has happened in the last few years, maybe 100 years. And some people would argue that, oh, this must be natural. But I want to show you that we actually know natural climate variation and we can understand it and we can predict natural climate variation. This all starts with a guy named Milutin Milankovitch. He's like some super nerd from Serbia. Uh, his research was like end of World War One through World War Two, I believe. I don't know, long time ago. Before computers and stuff, this guy did everything on paper with a really sharp pencil. Unbelievable accomplishment. This is debatably the most fancy math that's ever been applied to astronomy. This guy spent his whole life trying to understand what could possibly change climate using math. And he would spend all night looking through a telescope and he would measure distances between objects in the solar system and he would record these in writing. Every night he would take measurements. And over the years, he noticed, like, wow, the moon's a little bit further, or the distance to Mars is changing, or whatever. And understanding the orbits of all the things in the solar system, and then understanding the changes in those distances, this guy punches everything into uh, big calculations, and he finds that there are sine waves that describe those changes, right? Like it's going up and then it goes down and then it goes up and then it goes down. And those sine waves match his data. So he thinks, huh, maybe I can explain this. And today we have validated all of his research using satellites and supercomputers and measurements on the Earth. We know that he was right. This guy discovered 3 irregularities in our orbit in the solar system. 3 things that are imperfect. And these explain changes in how much sunlight reaches the Earth, which explain changes in climate. watch this. I'm gonna try. I know that we're looking on different screens. So on my big screen, this is really obvious. On yours, you might have to look really closely, but I'd like you to look carefully here. One thing that he found is that the shape of the Earth's orbit changes, and you have to know this. It's called eccentricity. So the shape of the orbit changes. If you look right where, let's see if I can get the laser pointer. Sorry, too much technology at once. But right there, the shape of our orbit changes. So for part of the orbit, we get a little further for the sun. And then after a few years, our orbits are a little tighter to the sun. And then after a few years, our orbits are a little further from the sun. So different amounts of sunlight reaches the Earth. That's called eccentricity, and that follows a long 100,000-year curve. Homeboy figured this out just by taking measurements and doing math on paper. We've now measured this using satellites, and he was right. Something else, this one in the middle, our axis wobbles. So the direction that the Earth is pointed actually changes on a 26,000 year cycle. 26,000. Finally, the actual angle of the Earth changes too. So that direction changes and the angle shifts. It gets a little bit steeper and then a little bit flatter. And that makes less pronounced seasons to more pronounced seasons. There's 3 cycles discovered by Milankovitch. They're called the Milankovitch cycles. 100,000 years eccentricity, 26,000 years precession. You can also call that axial wobble. That's actually a term. And then 40,000 year, it's called obliquity, which is the angle. Those 3, why can't I change my slide? Sorry. Those 3 cycles, the changes in the shape of the orbit, the wobble of the axis, and the change in the axis, each have a different impact on how much sunlight reaches the Earth. So you can graph them. It's on the screen now. There's the precession, obliquity, and eccentricity. And if you look at those 3 graphs, you can see that some cycles might be on a heating trend, while in other cycles on a cooling trend, those would cancel out. Every now and then, you're at peak of precession, plus peak of obliquity, plus peak of eccentricity. When you add all 3 cycles at the right moment, that's going to make a really warm planet because you have more radiation from all 3 reaching the Earth, more sunlight reaching the Earth. Sometimes you're at a low point for all 3 cycles. That is a cool period on the Earth. So the 3 cycles that Milankovitch discovered sometimes cancel out, but sometimes they add up. And those moments when they all add up, that's when we get big spikes or big drops in global climate. You can go back through all of our history of climate change, and these lines match up. There's a few exceptions. So another thing that changes the climate that's not Milankovitch cycles is like tectonic events. So if we get hit by a meteor or a supervolcano goes off, that could affect our climate, and that's not caused by sunlight. That's an internal change in the atmosphere, right? And there are other cycles that we've now discovered on top of Milankovitch. So in addition to the Milankovitch cycles, we now know that like solar flares follow a rhythm, or sometimes at extreme temperatures, there are changes in carbon cycling. So like when the planet dries out, more carbon leaves sediment and goes to the atmosphere. Anyway, we know other things that can impact climate. Some stuff is totally over my head, but these are known natural factors, primarily Milankovitch cycles, Also tectonic cycles, solar flares, carbon stuff. And there's no explanation with natural causes for what's happened in the last 100 to 150 years. There is no natural explanation that can capture what we know is happening with temperature. We do know that natural explanations explain the past. Ice ages, interglacial periods, we can explain those. Really dramatic changes sometimes. Meteor strike or volcano, we can find that evidence. But right now, our temperature, here's that temperature. Our temperature is spiking. It's going nuts. And that does correlate with a spike in CO2 and a spike in methane, which we know are being made by humans. I put this in all caps because I want to make a really loud point because I'm arguing with somebody who's not even here. But natural cycles would have us cooling. We're about halfway through a long-term cooling trend. Our planet has been getting colder for about 6,000 years, and we are heading into a little ice age in terms of natural forces. We should still be cooling for at least a few more thousand years. But obviously we're not. Obviously we're getting extremely warmer, extremely fast. And we know that's not natural. We know what natural cycles would be doing, and they would not be heating, they would be cooling. So we still have not come up with an explanation, but you kind of know where I'm getting at, right? I'm going to stop here, cover some more basics about the atmosphere, and then we're going to seal the deal in a couple more study goals.